In this video, we'll be confronting some of the usual suspects for mass flow network-based infiltration studies. My prior video introduced facilities implementing a virtual blower door test within a mass flow network in order to arrive at a set of calibrated orifices to match that blower door test flow. In this video, we explore the patterns of airflow that might result from those calibrated orifices as we cycle through different site wind exposures and sheltering. The context of this video is also single-level 4-room building. The building composition roughly follows the requirements of passive house, so the building sections are seriously thick and thermal bridges are constrained. There are a diversified schedule of occupants, lighting, and small power loads, and there is a simple environmental control that maintains a 20 to 24 degrees C environment during office hours, otherwise free-floating. My experience says that these rooms will require minimum heating and will have a tendency to retain heat from solar and internal heat gains, but that these are likely to be managed by natural ventilation or the occasional mechanical cooling system. For this study, which is focused on the impact of unintended air movement, the model will not include the usual MVHR kit or operable windows. Overlaid over the wireframe of the building is the network of nodes, components, and linkages that represent infiltration and inter-room air movement. A numerical approach which calculates infiltration and inter-room airflow will certainly be differently sensitive to weather patterns and how the building is used and controlled than, say, an approach relying on user-imposed airflow. Before we get into that comparison, let's first get used to the patterns of flow from the numerical approach. My prior video was based on a 1.2 air change per hour at 50 pascals flow test. This is somewhat shy of the requirements of passive house and rather better than the current UK best practice or the performance hoped for in the current building standards. Here's a slide from a BRE presentation I used in my passive house workshops to visualize blower door pressure test results. Visualizing folk drilling a coin-shaped patterns of holes in a facade is a rather stark reminder of the extent of snagging one might observe on site. For those of you who are unfamiliar with the term snagging, it refers to a legion of minor faults that no one can be bothered to sort out. Back to the physics. As the energy balance of a facade becomes less dominated by conduction, other paths, such as those related to unintended air leakage paths, play a bigger role. So, let's confront the first suspect: the loving or ignoring of data mining. When we commission a multi-domain simulation, the solvers work cooperatively as the assessment proceeds. A change in the energy or mass flow path ripples outwards and impacts the other solvers at the next time step. As the simulation progresses, the state of every element in that model at each time step can be archived into what might be a potentially vast data store. Of course, users might decide that only the usual suspects are required to be stored and reviewed. As we'll shortly find out, there's a lot more to performance than the usual suspects. To understand infiltration airflow impacts, here's the list of metrics I am using. I came up with this list after a series of interactive sessions with the ESP-RES facility. Once I got a sense of the kind of metrics that might explain the impact of infiltration, I of course automated the data mining process. I am using a visual comparison tool called MELD to look at two different reports, one on the left being in open countryside and the right city center. What we see is for each topic, we have maximum, minimum, mean, standard deviation for each zone in turn, and then a summary for all of them. And this happens for zone dry bulb temperature, resultant temperature, sensible heating load, sensible cooling load. And so I'm looking at the differences, the highlighted in blue from the left to the right, in order to make a judgment. Below this is a section related to sensible heating and cooling in terms of kilowatt hours over the period, kilowatt hours per square meter, hours required. And then just below that, there's two lines, hours when heating is required in at least one zone and hours when cooling is required. And that's a useful, interesting comparison. Below that is energy balances for each of the zones in turn. And we start with the infiltration and ventilation load, looking at the magnitude of that against all the other gains and losses over the period. Below that is a monthly selection of some gains and losses for each zone and each month. At the bottom of that is a summation for all the zones. Next comes frequency bin, in this case of zone dry bulb temperature. How often was it in each particular temperature band? So for each of the runs I made, these are the kind of comparisons I would do to see if there were some patterns emerging. Of course, beyond statistics, there are time step values of temperature, flux, and flow which can enrich the story. Our second suspect is choosing when to look. Some of the most telling patterns emerge in the context of events which demonstrate some classic scenario that I, as a simulationist, or my client might recognize. Say, for environmental controls, a Monday morning startup, well, that's a classic. We can learn a lot from that. With a high-performance facade, one might normally expect not much of a temperature drop overnight. Perhaps the degree for the environmental system to work back from. But I've often measured a 4 or 5 degree temperature drop overnight in a building with the same kind of insulation levels as that in Passive House, but which are only code compliant to a blower door test. For infiltration, surely the classic scenarios one might look at would be periods when wind speeds are exceptionally strong or almost calm, as well as periods where we get frequent changes in wind direction. So, looking at this graph of wind speeds over the year for a place called Hemsby in the UK, we see that winter has a tendency for higher wind speeds. If we drill down a little bit, this May week includes periods when the wind directions are changing and the wind speeds are historically low. And here's something that might give our environmental system a Monday morning startup issue, a windy January week. And now to our third suspect, the importance of the building site. Inevitably, site conditions differ from weather monitoring locations. Empirical methods demand a context, such as whether the site is open flat country with, say, some wind shielding, urban, or some city center locations. Assuming the wind is as measured, well, that's one comparator we ought to include. Here are the site variants I have used in this study. And now, a spoiler. Modeling choices do make a difference, but you have to look for those differences. So here's a top-level summary for you accountants out there that I extracted from some of the original reporting that we scrolled through. What do I see? The annual peak dry bulb temperature anywhere in the building, that's not particularly sensitive to site exposure. Resultant temperatures, they follow a similar pattern. The peak heating capacity gradually declines as we move toward a city center, while peak cooling is relatively insensitive. Where we do see differences in the heating demand over time and in the number of hours that heating is needed. Cooling demand over time increases as we move to a city center site, as do the number of hours of cooling required. Okay, that's the annual numbers. Let's look at that January week with high winds. Looking at the table, the dry bulb temperature peak during the week is insensitive, but the minimum is sensitive. A similar pattern is seen in resultant temperature. Peak heating capacity is sensitive to wind speeds, as is the heating demand over time. The number of hours heating is needed essentially halves as the site becomes more sheltered. The winds tend to be lighter in the summer, so here we see the metrics in the context of a week in May. Dry bulb resultant temperatures of the week, largely insensitive. Cooling capacity, cooling demand over time goes up as we shift toward that center city, and the number of hours when cooling changes very little actually. The fourth suspect is really not drilling down to individual rooms. We see that there's not a great deal of difference in the cooling with different sites. However, the heating certainly does change. Here is an example of how swings in wind direction cause facade leakage to evolve from infiltration to exfiltration over the period of a few hours, how that influences the energy impact on windward and leeward rooms. Zooming out to a week with quite a few hours of high winds and some directional changes, the volume flows in and out of each room, and they vary considerably. There are blips just after hour 85 and hour 133, where the change in direction has an impact. Below that, the table shows flows into and out of each room over that week. The rooms Box A and Box B are south-facing and are the subject of a rather more inflows than outflows, while Box C and D, the flows are predominantly exfiltration. Graphs of individual flows are not the only approach. We can also plot the flows between each of the nodes and components at each time step in a three-dimensional view. Yeah, it takes a bit to get used to. It's a bit primitive, but it sometimes is able to clarify flow paths and how they change over time. So for each of the runs I made, these are the kind of comparisons I would do to see if there were some patterns emerging. Why bother looking? Well, say a group is rolling out a standard building design across a number of sites in a region, and those different sites have different wind exposures. Facilities managers might have an interest to see if those different locations are going to have different running costs or deliver not tenant comfort, but a rolling string of complaints.